lecture on intermolecular forces. So let's go over some of the intermolecular forces that we've talked about so far. The most strongest one is ionic. Okay, this is where two charges have literally come together and attract. Okay, you know, positives attract with negatives. Okay, and then we have some molecules that have a dipole force. Okay, or dipole moment. Okay, and we call those types of molecules polar. Okay, one end of the molecule is partial. Okay, the key word here is partial. Okay, not full, which is the full charge of ionic, full positive attracting to full negative. It's a partial positive attracted to a partial negative. And then within that subgroup, within the subgroup of the dipole moment polar molecules, we have those that are polar, but they can also hydrogen bond. Okay, this is a very big deal, especially if you take the biochem or the other chemistry classes, or more the biology side, hydrogen bonds. So for a hydrogen bond, we're going to look for an OH, hydrogen bonded to another hydrogen. We're looking for an NH anywhere in the molecule, hydrogen bonded to another hydrogen, and then we're looking for a fluorine, hydrogen bonded to another hydrogen. Right, and then we have something called dispersion. And this is also called London dispersion forces. So these, we're going to be looking for what type of molecules? These will be looking for the nonpolar, right? Do we remember from Wednesday? Okay, what functional group are nonpolar? Okay, these would be the hydrocarbons, and they're called the alkanes: methane, ethane, propane, butane, pentane, the alkanes. So these are very, very weak. Okay, do we remember this from Wednesday? They're very weak. So just take some butane, okay, and splay it out on the surface. It's gone. Okay, it's just going to evaporate very, very fast. Right. Pentane. Okay. Even take gasoline. I believe if you take gasoline and just put it out on the road, it'll just evaporate into the air, the atmosphere. Okay, that's just the very nature. Those molecules have very weak intermolecular forces, so they just evaporate very fast. A couple of other things here. We can also have an ion-dipole interaction. Okay, something I did not cover, but there's something called ion-dipole. Okay, it's very simple. It's an ion with a dipole. Okay. So what would be an example of an ion that we learned in Chem 1? Maybe something like sodium ion. Okay, what is an example of a molecule that's polar? We talked about this yesterday, water. Okay, water is a polar molecule, so this is full positive. But if we remember our structure of water, H2O, but H2O is not HOH. Okay, it's the two H's, my left and right hand. They bend. Okay, they bend like this. Okay, making the molecule structure bent. This oxygen is electronegative, giving it a partial negative, partial. Okay, that delta minus means partial negative. Same on the other side. And what does that leave these hydrogens? It leaves these hydrogens partial positive. Very good. Okay, so this is a molecule water. Here are our two lone pairs. Okay, here is our molecule of water, which is polar. You can see the net dipole moment, partial negative with partial positive. Here's a sodium ion. Do you remember from Chem 1, sodium, if it were to form an ion, would like to be +1. So this is the ion. Okay, this is the dipole. Okay, and you have a attraction between the full positive and the partial negative. We'll highlight that in yellow for us. Full positive, partial negative. Okay. That's going to be an ion-dipole type of interaction. Remember, this partial negative can attract anything positive, whether it's a partial positive or a full positive. Okay, so this is called an ion-dipole intermolecular force. Ion dipole. Okay. So water has this remarkable ability. If we'll learn, if you take the biochem or the higher chemistries, water has this remarkable ability to solvate. Or having solvation shell is another term we used in the higher chemistry classes. It's solvated, literally, water here, water here, water here, water here, literally surrounds the sodium ion. It will literally surround the potassium ion. The potassium channel, it won the 2003, I believe, Nobel Prize in Medicine. So that lab solved the potassium channel, which is all over the cells in our body. And he determined that the water will form a shell around the potassium, and then it goes down, another water will form a shell, and another 4 or 5 waters form a shell, so like that until it gets inside your cell. So water can do that. This is an ion-dipole interaction. All right, we talked about hydrogen bonding here. Okay, so, okay. All right, so ion-dipole forces are on this page. And these are dispersion forces. So dispersion forces, just to realize, are nonpolar, very weak, and they're caused by circulating electron clouds. Okay, so that's dispersion forces. The ion dipole forces is what you see here. So this is ion dipole. I guess it would help read my notes if I'm writing. Here it's ion dipole, and I'm writing ion dipole here where it's supposed to be dispersion. So this means it's Friday, right? So ion dipole goes here, dispersion, it's just very weak, and it just goes very rapidly. Okay, it evaporates because the intermolecular forces are so weak. Again, alkanes and anything nonpolar. Okay, so that's dispersion. Ion dipole. Okay, this is dispersion. Ion dipole. Go back to page 4 of our notes. Okay, see page 4. Hydrogen bonds. Let's go to page 6 here. I want to show you something about hydrogen bonds. Right. I know it may be hard to see, so that's okay. I'm going to try to zoom in on here. And it's hard to see. It's even harder to see because of this. Let me try to autofocus. Worst projector in the world. Okay. So remember, for hydrogen bondings, what are we looking for? Okay, OH, NH, or the element fluorine, which is F. Very good. Okay, so we have 2 molecules here. All right, it's hard to see, I know. We have water and water. Okay, let's look at here, water and water. So look at, we have this oxygen, and then we have this hydrogen, and then we have this hydrogen on the second molecule. Okay. So we have HO, and that's the hydrogen bond with the other H. Okay, so there is your hydrogen bond. there is your hydrogen bond. HOH. Okay. HOH. This H comes from a second molecule of water. Okay, here we have an NH. Okay. And look at here, look at that 3 dots, which is your hydrogen bond. HNH. HNH. Okay, that H here belongs to a second molecule, okay, in the intermolecular forces. Okay, so NH3 is ammonia. This is ammonia. Okay, H2O is water. How about H2O and ammonia? Can they hydrogen bond? Okay, here's your hydrogen bond, those 3 dots. We have HON. HOH, I'm sorry, HOH. Okay, HOH. Okay, this H is coming from the second molecule. This H here is coming from the second molecule. This H here is coming from a second molecule. So HO, the second molecule provides the H, partial negative with partial positive. HNH, this hydrogen is coming from a second molecule, partial positive with a partial negative. HON, this hydrogen here coming from a second molecule, partial positive with the partial negative. And then we can move on here. Here we have NH3 and water. NHO. NHO. Okay. NHO, you see that hydrogen is from a second molecule. Okay, these are their hydrogen bonding patterns. Here we have an HFH. Okay. This H is a second molecule. Okay, this fluorine will be partial negative. This oxygen partial negative, nitrogen partial negative, nitrogen partial negative. What is that hydrogen going to be? Partial positive. The hydrogen that forms the bridge will be partial positive. And then we have NHF. NHF. Okay. This H again is from a second molecule in the second molecule hydrogen bonding to another molecule. This H is going to be partial positive. This nitrogen is going to be partial negative. Okay, so HOH, NHH, HOH, NHO, HFH, NHF. Okay, so we're having sort of a network of hydrogen bonds. Okay, it's a special type of attraction. So remember, a hydrogen bond is an attraction. It's a very strong attraction, not a repulsion. It's an attraction, and it's also not a bond. It's a strong attraction. Okay, in biology they may say hydrogen bonding is weak in your biology class, but in chemistry we call it strong. Okay? Strongest of all is a covalent bond because that's sharing. You know, a double bond, single bond, triple bond. But here in this context, hydrogen bonding is strong, definitely stronger than dispersion. So that is hydrogen bonding. So, you know, this can go on and on and on all throughout space, this hydrogen bonding network. You see these 3 dots? These 3 dots can go up, down, behind the projector, up the projector, in all 3-dimensional space. So that is hydrogen bonding. All right, let's move on to our next page here. So OH, if you see that anywhere in the molecule, NH, if you see that anywhere in the molecule, and F, if you see that anywhere in the molecule. Okay, we are talking about hydrogen bonding. So on the test, hydrogen bonding, look for OH, NH, or F. Really what you want to do is draw the structure. Okay, once you draw the structure, you see an OH, NH, or F in the structure, then it's going to hydrogen bond. Okay, and you want to make sure the molecule is polar. All right, let's look at this table together before we do some practice problems. Okay. All right, so you don't need to know all these chemicals. This is just organic chemistry. So that little tip here represents a carbon. Okay, yeah. Excuse me. That little tip there represents a carbon. Hold on. Okay, that tip here represents a carbon. This tip here represents a carbon. And I'll just fill them up with hydrogens. You don't need to know this because this is really organic chemistry. Okay, that tip here represents a carbon. I'll fill it up with hydrogens. Okay, this tip represents a carbon. Okay, and we'll fill it up with hydrogens. Okay, like I said, don't worry about reading all of that. What I want to focus your attention on are the boiling points. So why do you think N,N-diethylamine, that's another functional group, the amines, why do you think it has a boiling point of 36? Is it polar or nonpolar? Okay, that nitrogen is going to pull on all sides. Okay, because it's pulling, it's electronegative, it's going to have a partial negative. Okay, and that makes it polar. Can it hydrogen bond? Okay, this nitrogen is bound to a carbon, the carbon, another carbon. Anytime you see a point, that's a carbon, and there's another carbon. So it cannot hydrogen bond. It's just a dipole-dipole, and that's why it has its boiling point at 36 degrees. Okay, what about this one? Can this hydrogen bond? Okay, we have not just an NH, but an NH2. This nitrogen is bound to this carbon, and can it hydrogen bond? Okay, by virtue of the NH, it can't hydrogen bond. So what reflects the higher boiling point? Okay, the fact that it can hydrogen bond. All right, and this example here, we have a positive and a negative. Positive and a negative. So a full positive with a full negative, what type of attraction is that? Ionic. So what will the boiling point of something that's held together by ionic compounds be? High. High, very good, high. And you see that here. Okay. What about this? Okay. What do you think about this molecule here? Okay. Remember, these points represents a carbon. Carbon and a carbon, we're going to fill it with hydrogens. So is this hydrogen bonding? Okay, the answer is no, because there's no OH, NH, or F. Okay. Can this hydrogen bond? Remember, this is a carbon, that's a carbon, that's a carbon, that's a carbon. Can this hydrogen bond? Yeah. Okay, how do you know it can hydrogen bond? The OH. Okay, and you see the positive charge and the negative charge. Okay, what do we call a full positive with a full negative? Ionic. And look at the boiling points. Okay. So now, if I give you 3 molecules, okay, or 3 compounds, and can you rank them based on the boiling point, highest to lowest? The answer is yes, it should be able to. Okay. What happens if I put here hexane? What do you think its boiling point would be? Hexane. 1, 2. Hexa is 6. So 1, 2, 3, 4, 5, 6. So what do you think its boiling point would be? How low? Okay, definitely lower than 80. Correct. Very good, Michael. It would definitely be lower than 80. Okay, so something like this, if I'll give you the chemicals, and immediately if you see it's nonpolar, like a hydrocarbon, alkanes, okay, this one happens to be hexane, that's the lowest boiling point. Okay, we will know that's the lowest boiling point. Which would have a lower boiling point, hexane or pentane. Instead of 6 carbons, we'll go with 5 carbons. 1, 2, 3, 4, 5. What is easier to break up in terms of intermolecular forces? Something that has 6 carbons or something that has 5 carbons? Easier to break up. 5. Okay. Easier to break up 5 than 6. Yeah.
How can you tell that hexane is non-polar? Like that.
Carbon and hydrogens are not electronegative. So we're looking really for oxygen, nitrogen, the halogens such as fluorine, the chlorine, the bromine. Those would be nonpolar. Okay. Carbon does not have a lot of sucking power, pulling power. It's not electronegative. Okay, so we're looking for the electronegative elements here. Carbon and hydrogen are very weak pullers, but these guys are strong pullers. Okay, iodine, the halogens, oxygen, okay. Well, if I have something like CO2, okay, are you Harrison? No. Okay. Okay, is this polar or non-polar? It has oxygens that are electronegative. It would be polar? What if I told you it was non-polar?
Oh, because it balances out.
Right. It balances out. They cancel each other out. And this pull cancels out that pull. So even though this is pulling that side, partial negative, what is it canceled by?
So like
the
when
one
it
going this.
the Lewis structure.
Right. Mm-hmm. Same thing. We gave an example. You're Allison? Yes, ma'am. Okay, CCl4. Wow, 4 chlorines. That's got to be super electronegative. It's not. Okay, why? It's got to be super polar. Why is it not super polar? It's super nonpolar because these chlorine poles cancel each other out. The answer to your question, Allison, yes, when in doubt, you need to draw the Lewis structures. Okay. Do you see that, Harrison?
Yeah.
So this would be nonpolar, even though it has 2 oxygens, and you're kind of thinking, oh my goodness, okay, it's polar. It's not polar. It has a dipole moment. Okay. So this would be nonpolar, and that would be nonpolar. Okay, so which would be here? Hexane or pentane? What do you think? Which would have the higher boiling point? Is it harder to break up 6 or is it harder to break up 5? If you have 6 people in a fight, it's a bad example, so I apologize. If you have 6 people in a fight versus 5 people in the fight, okay, what's easier to break up? It's easier to break up 6 people? Wow. Right, it's easier, in my mind, I think easier to break up 5 people. Right? I think so. Okay. So usually more mass, more intermolecular forces. Okay, more mass, more intermolecular forces. Yeah, go ahead.
So pentane has the higher boiling point?
Hexane would.
Okay.
It takes more to boil it. So which would have a higher intermolecular forces, hexane or pentane? Which would have more intermolecular forces? Hexane. Okay, so more mass, more intermolecular forces to overcome, and that implies a higher boiling point. Okay, more IMF to overcome. And all of this means higher boiling point. Coming back to this example, this has 6 carbons. Can you imagine a hexane interacting with a hexane versus a pentane interacting with a pentane? Okay, what is easier to break apart? What's easier for them to disrupt those intermolecular forces? Okay, you overcome less intermolecular forces when you have 5 carbons as opposed to 6 carbons. Okay. All right. So more mass, more intermolecular forces to overcome. Okay, what about methanol? What would you see here? Okay, so this would be the lowest, and then second lowest, where would methanol be? Methanol can hydrogen bond, but then it can hydrogen bond, but so can butyric acid. So which do you think would have the higher boiling point, butyric acid or simple methanol? Which would be higher and which would be lower? Which would be higher? Correct. Based on what? Okay. Molecular weight. Okay, based on molecular weight. Okay, so this probably I would go, but it can hydrogen bond, so 3. This is kind of tough. This is heavier, but it's polar, cannot hydrogen bond. This is kind of a tie. I really don't know. I got to look at the literature for that. But then this would be definitely second highest. This is the highest. Okay. So this is something I got to look at a textbook or something. The boiling point in this, because this can hydrogen bond, but this is polar. This is heavier than this. Who wins? I'm not entirely sure. Usually hydrogen bonding is a lot more powerful than just the plain molecular weight. If I were to guess, I would say this has a higher boiling point than that, but I'm not entirely sure. Okay, this is hydrogen bonding. This is just polar. So that's how we kind of use intermolecular forces to guess the boiling points, to guess the melting points, knowing nothing. Just knowing, as you mentioned here, the structure. Knowing absolutely nothing, just knowing the structure, we should be able to predict and rank how these things will fall in terms of boiling points.
Do the electronegative elements mean non-polar?
No, they mean polar. They mean they pull. Pull. So if you have anything with an oxygen bound, it's going to pull. It's going to pull. This nitrogen will pull, a fluorine will pull. Okay, chlorine will pull. If you look at hydrochloric acid, this chlorine is going to pull. Okay, it pulls so much, it's so electronegative, it actually cuts and gives you a proton. So these are elements that pull. And so they make the molecule more polar. They make the molecule more polar, unless they cancel each other out, right? Like here and here. All right, let's do some practice problems together. Okay, page 8 here of our notes. All right, how are we on time?
1:30.
Okay, got 20 more minutes. All right, so let's hang tight for another 20 minutes. All right, let's do this problem together here. Which of the following species are capable of hydrogen bonding amongst themselves? Okay, with themselves, not with another molecule, with themselves. So what do you guys think here? Hydrogen sulfide, yes or no? No. Okay, hydrogen sulfide would not. Okay, this is hydrogen sulfide. Okay, what about benzene? Do you guys know the structure of C6H6 benzene? Do you remember this from Chem 1? Yes? Yes, we do? No, we don't?
Oh, it's a ring.
Yeah, it's a ring. Okay, good. Okay, it's a ring, and then we fill it up with hydrogens. Okay, there's some double bonds here. Okay, so instead of putting those carbons like that, we can make that carbon a point. Point, another carbon point, third carbon point, that carbon point, this carbon point, that carbon point. Okay, we can make them into a point. Okay, and then we'll add our double bonds. So this is C6H6. I'll add the hydrogens, though a lot of people don't even bother putting the hydrogens. All right, knowing the structure is this for benzene, what do you think? Is it hydrogen bonding or no hydrogen bonding? None. Okay, what do you think? What do you think is the main IMF for benzene? Huh? Dispersion. London dispersion forces. Very good. Okay. Okay. What do you think the main IMF for hydrogen sulfide is? It's not H2O, but H2S. Okay, so what do you think the main IMF is for this? For hydrogen sulfide part A? Dipole would be what it'd be, but not hydrogen bonding. Okay, part C, this is called methanol. What do you guys think about methanol? Yes. And what type of functional group does methanol belong to? Functional group. It's an alcohol. Alcohol. Okay, that's what methanol is. It's a type of alcohol. What do all alcohols have? What do they all have? OH. Okay. Okay, so you can replace the R with any type of carbon compound. And then that's how you get your methanol, ethanol, propanol, butanol, pentanol, hexanol, septanol, octanol, so on and so forth. Okay? So these are the alcohols. Okay, which of the following can form hydrogen bonding with water? Okay, not with itself, but with water. Okay, this one, dimethyl ether. What do you guys think? Can it hydrogen bond with water? Yes or no? Yes is the right answer. Very good. Okay, yes. So I'll just put the little dots here. Okay, this is partial positive, partial negative. There's a partial positive. This oxygen pulls on this carbon. Okay, this oxygen pulls on this carbon. That makes it partial negative. This carbon is partial positive. Okay, and we have here, like we saw beforehand, OHO. Okay, OHO. This H is the bridge, okay? By the way, CH3OCH3 looks like this, okay? We draw it like this, or we write it like this. Okay, what functional group is this molecule? Ether. Ether is the right answer. Ether, okay? Ether. I do not know what they use for anesthesia now, but I think back then they used ether, okay? In the old days in the hospital clinics, ether. Okay, this is the functional group for ether. All right, good job, you guys. All right, very nice work. All right, what about part B? Methane. No is the answer, okay? Methane is CH4. Okay, what type of molecule is methane? Is it polar or nonpolar? Methane, CH4. What type of molecule is methane? Polar or nonpolar?
No.
What type of functional group is a methane? Alkane. Alkane. Methane, ethane, propane, butane, pentane. These are alkanes. Okay? So this specific alkane is called methane, CH4. It's a hydrocarbon. And is it polar or nonpolar? Nonpolar. Water is polar, and it cannot form hydrogen bonding. Okay? Can they mix? Are they miscible? Methane and water, are they miscible? No. They would be immiscible. Okay, why are they immiscible?
Because the nonpolar, it's not polar, so it won't mix with water.
It's nonpolar, so it won't mix with water, is correct. Okay, what about this? Miscible or immiscible? Miscible, why is that? Why is it miscible? Because both are polar, okay? So let's remember something here. I'd like for you to know these three words. I'd like for you to know like dissolves like. Like dissolves like. Okay, like dissolves like. What does like dissolve like mean? Okay, a polar molecule will dissolve with what? Polar. Non-polar molecule will dissolve with a non-polar molecule. A polar molecule and a non-polar molecule, they're like oil and water. Okay? Okay, water, it would be the polar. The oil that we did in class the other day would be non-polar. So they just get away from each other. They segregate. All right, how about part C here? Fluorine, what do you think? Yes? Can it hydrogen bond with water? What do you think? Are you sure, Alex? No? I got a no and a yes. What do you think? What did you say earlier in the class? What should we do? We should draw the structure, okay? Okay, do we remember how to draw fluorine? F2? It's just like O2. And what will this fluorine do? It pulls that way. And what will this fluorine do? It pulls the other way. Okay, so we have a partial negative here. And what is that balanced out by or countered by? The other fluorine. So would this be polar or nonpolar? And we all know water can not only hydrogen bond. The reason why it can hydrogen bond is because it's polar. So this cannot hydrogen bond. So this can hydrogen bond, this cannot hydrogen bond, this cannot hydrogen bond. Miscible or immiscible? Taking some fluorine, and will it dissolve in water? Immiscible. Okay. How about part D here? HCOOH. Would you guys like to know another functional group? Okay, these are called the carboxylic acids. Have you heard of carboxylic acids? I think they're found in some perfumes, and well, they're everywhere. Okay, so this one is called formic acid, and the carboxylic acids will look like this: RCOOH. Carboxylic acids. This is not something. I mean, it's good if you know it. It will help you out. But for now, this is another functional group, the carboxylic acid. Remember, these are the ethers, and these are the alcohols. All right, can this hydrogen bond with water? Yes. Okay. Okay, so it can hydrogen bond. And check this out. It's going to be OHO. Okay. OHO. Okay. That would be your hydrogen bonding pattern. Partial positive, the partial negative. Okay. Yeah. OHO. Wait, miscible or immiscible? Miscible. Okay, and finally, part E. Can this form hydrogen bonding with water? Na+. Na plus sodium ion. Can it form a hydrogen bond with water? No. No hydrogen bond. Okay, what type of attraction would it be? This is an ion. Water is polar, it has a dipole moment. This actually is not hydrogen bonding, but it's ion dipole. So do we expect this to be miscible or immiscible? Miscible or immiscible? Don't we have sodium in our bodies, sodium ion? Don't you drink Gatorade? Okay, or what are those energy drinks? So miscible is the right answer. Okay. The ion is just a full positive charge. The dipole would be a partial. The dipole would be a partial positive with a partial negative. So the dipole is partial, not full, whereas the ion dipole is the full from the ion and the partial from the polar molecule. Ion dipole is this. Here's the ion, here's the dipole from the water. But dipole is this. Here's the dipole from this molecule, here's the dipole from water. That's your hydrogen bond. Now this is not a hydrogen bond, this is just an ion with the dipole from water. This is the dipole from formic acid, which is a type of carboxylic acid. Partial positive attracting with the partial negative from the dipole of water. It's a good question. What's the time we have?
1:45.
Okay, 1:45. I'd like for you guys to know these 4 properties of liquids. Okay. One of them is surface tension. The other one is viscosity. And then the other one is adhesion and cohesion. Okay, just know them, just memorize them. Okay, like a good multiple choice question on the exam. Okay. any type of liquids. It's not just water. It could be blood. It could be It could be salt water. It could be anything. Okay? Any type of liquid. Okay, urine. Okay, urine. They test the viscosity of urine for the medical doctors. Okay, for diseases and errors in metabolism, so on and so forth. So, what is surface tension? Okay, surface tension is that on the surface of an air-water interface, okay, air or any type of gas interface, okay, water, any type of liquid interface, okay, right on the surface between the gas and the liquid, right on the surface, there's some extra, little stronger IMF. Okay, the IMF is a little bit stronger. Okay. So we actually see this in the lungs. I did my research on this, on the air-water interface in the lungs. Do you know lung surfactant? If you're born premature, you don't produce lung surfactant, which minimizes this surface tension at the air-water interface in the lungs. But for now, all you need to know is right on the surface, the intermolecular forces are stronger or weaker. Okay, right at the bridge, okay, the interface between the bulk air, bulk gas, and below the bulk liquid. Okay, the lung is the air-water interface for me, but any type of gas-liquid interface, the liquid intermolecular forces are tighter. And if it's water, the hydrogen bonds are a little bit tighter. Okay, they're packed. Molecules are packed more like sardines. Okay, viscosity is resistance to flow. Okay, so one property that all liquids have is surface tension. Another property is viscosity. Okay, I'll give you one more minute here. Okay, viscosity is resistance to flow. Okay, think of syrup, think of molasses, think of water. Okay, how do they flow? One flows like a goop, the other one flows smoothly. All liquids have that. And then adhesion and cohesion. So adhesion is what gives rise to, so this is liquid to the gas, liquid to the container, okay? It's like a pull. Okay, liquid to the container. Have you ever done a glucose prick to test for sugar? How does the blood go? Into the strip. Okay, that's capillary action, and that is adhesion. Okay, the blood, remember, any liquid, and blood is a liquid, has surface tension, viscosity, and it could adhere, and that's causing this to literally just sucked into the glucose strip. Okay, so that's adhesion. You just need to know adhesion, and just know cohesion. Okay, cohesion also is this. It's between like molecules, and this gives rise to the meniscus. Okay, that you often see on the surface of the glass. Okay. Anyways, what are the three properties of liquids? Surface tension, all liquids. Viscosity, and then what's the other one? Adhesion, and the fourth one? Cohesion. Okay? Adhesion, cohesion, surface tension, and viscosity. All liquids have this. Have a good weekend. Try to work on your homeworks. Slowly and surely, I think I put a due date up, but I think I made it next Saturday or next Friday. Anyway, start working on that slowly.